Digital signature is the main application of asymmetric encryption. As we are going to see, a digital signature uses a hash function to produce the fingerprint of the message. And this fingerprint is signed with the private key of the individual who created the message. This signed fingerprint is the digital signature. In this video, I will only give the general scheme to create a digital signature. I will not go into the details of this or that signing algorithm. I will merely talk about the properties of digital signatures. So before I start presenting the digital signature, let me immediately clarify one point. Associating a marker, such as a JPEG representation of a person's handwritten signature, as shown on this slide, does not create a digital signature. This JPEG representation of a person's handwritten signature is what we call an electronic signature. Electronic signatures do not use cryptography and are easy to alter and forge. However, electronic signatures may suffice in some applications. A digital signature is a cryptographic technique that guarantees the authenticity of data. And more precisely, a digital signature guarantees the identity of the signer, this is the authentication property, and the fact that the data has not been modified since it was sent, and this is the integrity protection. So one thing you would probably say is, wait, these are exactly the properties of a Mac. Yes, it's true. These are the properties of a Mac. However, there are some differences between a Mac and a digital signature. We will discover these differences step by step. Formally, a digital signature system is a pair of algorithms, S, V, where S is the signing algorithm and V is the verifying algorithm. The signing algorithm takes as input a private key and a message and outputs a signature. The verifying algorithm takes as input a public key, a message, and a signature, and outputs true if the signature corresponds to the message, and false otherwise. A signature is secure if it's impossible for an active attacker to forge a valid pair, message, and corresponding signature without knowing the private key. In practice, the signing algorithm is not applied on the message M, but on the fingerprint of the message M, computed with a hash function, mostly for efficiency reasons, but not only. There are different signing algorithms, but in the remainder of this video and in the remainder of this course, I will use an asymmetric encryption algorithm, for example RSA, as a signing algorithm. Under this hypothesis, digitally signing a message consists of computing the fingerprint of the message to be signed and encrypting the fingerprint with the private key of the individual who created the message. Let me show you how Bob can digitally sign the message he wants to send to Alice. On this slide, I suppose that the message to be signed is not encrypted. It's plain text data. Bob computes the fingerprint of the message using a hash function. Using asymmetric encryption, Bob encrypts the fingerprint with his private key. The encrypted fingerprint is the digital signature. Bob sends Alice the message and the signature appended to it. So the message is not encrypted and the digital signature is simply appended to the message. To verify the signature, Alice first separates the signature from the message. Then Alice computes the fingerprint of the message. Using Bob's public key, Alice decrypts the signature. Alice verifies that the two fingerprints are equal. If they are equal, then Alice has proof that the message came from Bob and that it has not been modified since it was sent. If the decrypted signature is different from the digest computed by Alice, it could mean one of the two things. Bob is not the person who sent the message, or the message was altered between the time it was signed by Bob and the time Alice verified the signature. Please note that a digital signature brings more security than a handwritten signature, simply because digital signatures are more difficult to forge than handwritten signatures. And digitally signed documents are more difficult to tamper with than signed paper documents. In a previous video, I presented asymmetric encryption, and this slide is from this previous video. I mentioned that one conceptual problem of asymmetric encryption is how can Alice be sure that the message sent by Bob actually comes from Bob, since any attacker can use Alice's public key. And I said that the solution relies on the digital signature. So I will now present this solution. Bob wants to send an encrypted message to Alice using asymmetric encryption. And Bob also wants to prove to Alice that he is the person who actually sent the message. First, Bob computes a fingerprint of the message with a hash function. Bob encrypts the fingerprint with his private key, creating the signature of the plain text. Bob appends the signature to the message. Bob uses Alice's public key to encrypt the message and the signature together. Verification goes as follows. Alice uses her private key to decrypt the message. Alice separates the signature from the message. Alice computes the fingerprint of the message. And Alice uses Bob's public key to decrypt the signature. Alice verifies that the decrypted signature matches the fingerprint she herself computed. Alice has proof that the encrypted message came from Bob. The first conceptual problem of asymmetric encryption is solved. The scheme I have just presented uses the approach sign and encrypt, which is considered better than encrypt and sign, or sign and encrypt. The main reason why the sign then encrypt scheme is better is that it is considered that the signer must know what is signing. The signature must therefore be computed from the plain text. One question that might come to mind is, can we use digital signatures instead of MACs when using symmetric encryption? From a theoretical point of view, answer is yes. However, verifying with MACs is faster than verifying with digital signatures. So I would say that if two parties are communicating using symmetric encryption, then it's much better to use the MAC. Now, consider the case of several parties communicating using symmetric encryption. If we need accurate authentication of messages, then we might consider using the digital signature instead of MAC, if we need to know exactly which party sent the message. I remind you that with a MAC, authenticating a message only proves that the message was sent by a party holding the secret key. If you read the literature on digital signatures, you will read that digital signatures provide the non-repudiation property. Non-repudiation means that an entity cannot deny having taken an action. Since digital signatures are publicly verifiable and authenticate a single entity originator of the message, they can serve as a means to implement non-repudiation. For example, if Alice digitally signs a message, then she cannot later deny having sent that message because everybody can verify the signature with Alice's public key. I would like to conclude this video by comparing the properties of the digital signature and the MAC. Both cryptographic constructs ensure message integrity. The digital signature ensures authentication since it proves the identity of the sender. The MAC ensures a weaker form of authentication. It authenticates one party to the other party in a two-party communication. In a multi-party communication, MAC only proves that the message was sent by an entity holding the secret key. Since the digital signature is publicly verifiable, it ensures a non-repudiation property. The MAC does not ensure this property because it is not publicly verifiable. Moreover, any entity that can verify the MAC is an entity holding the secret symmetric key, and as a result, this entity could forge MAC values. In this video, I presented digital signatures. The digital signature is a very important cryptographic construct. As we will see later in this course, digital signatures can be used to authenticate parties in the Diffie-Hellman protocol, preventing the man-in-the-middle attack intercepting and relaying messages between the communicating parties. In addition, the digital signature provides that important property of non-repudiation that the MAC cannot provide.